Hello, I am Gautam and today we will discuss about valence shell electron pair theory, that is VSEPR theory. So, what is VSEPR theory? In one words, the VSEPR theory is the old covalent bonding theory. Yes, this is the old covalent bonding theory. So, what is the utility of this theory? This theory is useful for the explanation of basic structure of a compound. The basic structure, only the basic structure. Okay. So, I will discuss about the 5 different rules which the VSEPR consists. So, let's begin. The 5 theory. 5 rules. The first rule says, if there is no lone pair on the central atom, then number of sigma bonding electron pairs will determine the geometry of the molecule and will be regular shaped. So what does this mean? This means if 2 sigma bond are present, then this structure will be linear structure. 3 sigma bond, trigonal planar. 4 sigma bond, tetrahedral. 5 sigma bond, trigonal bipyramidal. 6 sigma bond, octahedral. So these 1, 2, 3, 4, 5, these 5 bonds, 5 sigma bonds, here in case of only sigma bonds, not 5 bonds or not any lone pair. So first rule says there is no lone pair present on the central atom. So if this occurs, then number of sigma bonds consider only the structure of the molecule or the structure of the compound. This is the first rule. And the second rule is, when central atom contain both lone pair and bond. So here in the first one only bond pair, no lone pair. But in the second case, that is second rule, both lone pair and bond pair. So in the case of both lone pair and bond pair, the second rule says when central atom contains both lone pair and bond pair, then the structure is deviated from the regular geometries. So this term, regular geometry, what this term means? The regular geometry term means these 5 geometry, which contains linear, trigonal bipyramidal, trigonal planar, tetrahedral, trigonal bipyramidal and octahedral. These are regular geometries. But when both lone pair and bond pair present, the regular geometry is deviated, and after deviation, what will we gain? We gain that the repulsion order of second rule can be explained by the example. What is the example? ClF3 example. So what is the structure of ClF3 and how we will explain it? This can be explained as, now Cl atom having electronic configuration 3s2 3p5, that is 7 valence electrons, and in the compound ClF3, 3f shares 3 cross 1 electrons, that is total 7 plus 10, sorry, 7 plus 3 electron, that is 10 electron. Now in the compound ClF3, only 3 sigma bond, that is 3 ClF single sigma bonds are present, which contains 3 cross 2 equals to 6 electrons, that is sigma electrons. And the left 10 minus 6, that is 4 electrons are left on the central atom, which is the 2 lone pairs on the central atom. These 2 lone pairs control the overall geometry of the molecule. So how it is controlled? Here the lone pair in this case, actually the 2 lone pair in this case, affects the structure by the repulsion with the bond pair. So lone pair repulsion is greater, lone pair bond pair repulsion is slightly lower, and bond pair repulsion is lowest. So this is more repulsion and this is less repulsion. Now when lone pair repulsion occurs, then the molecule becomes destabilized, and this, in this case, slightly stable structure is formed. So for the ClF3 atom, for the ClF3 structure, for the ClF3 compounds, there are 3 possible arrangements possible, with 2 lone pair and 3 bond pair, sigma bond pair. Now 3 bond, sigma bond, and 2 lone pair, there are 3 possibilities of the structure. So what will be the ClF3 structure? The ClF3 will show TBP, that is trigonal bipyramidal structure. But why? Because 3 sigma bond and 2 lone pair, that is total, actually we can say there is total 5 sigma bond or 5 bond, considering lone pair as a bond, 1 lone pair as a bond. So 5 bond or 5 lone pair or 5 bond can form trigonal bipyramidal structure, but this will be distorted or slightly deviate from the structure if the lone pairs are not easily arranged. Okay, let me see you. There are 3 possibilities. Let's draw the possibility. First case, F lone pair F. Second case, lone pair F, and the third case, lone pair F lone pair. So maximum repulsion occur when the lone pair distance angle between lone pair and the bond pair means ClF and lone pair means Cl lone pair bond. So the maximum repulsion occurs when the lone pair and bond pair angle will be less. So the lone pair and bond pair angle will be less here and here, only here. There is lone pair bond pair repulsion less, lone pair there is 290 degree lone pair bond pair angle and 190 degree angle with lone pair, that is more repulsion, that is this system is not stabilized, this is destabilized, so this is not possible structure. In this case there are 2 lone pairs with the 3 bond pairs at 90 degree angle, all are in 90 degree angle except the 3 bond pairs itself. So there is, in this case there is also more destabilization. So this is also not possible. But in this case, this structure is possible. Why? Because in this structure, the two lone pairs are on one plane, that is 120 degree, and the other lone pair bond pair angle is greater than other two cases. So this structure is more stable than the other two. So this structure is accepted instead of this and this. Okay. So now we will discuss about the structure, which is structure about this, and which is T-shaped. Why is it is T-shaped? Shape, we tell about shape, difference between shape and structure. When considering when we tell about structure, we will not consider we will consider the lone pair, but when we say about the shape, we will not consider the lone pair. So ignoring the lone pair, we get the 3Cl and 3F atom which are in T-shaped. So it is T-shaped structure, and it is accepted. Now we will tell about the third rule, which is about the electronegativity difference of the different atom in a compound. So let me explain this. So we start this with an example, that Pi3, PBr3, PCl3, PF3 and PH3. These 5 compound have one lone pair on the phosphorus atom in each case, and iodine, bromine, chlorine, fluorine and hydrogen atom. So this compound forms 3D tetrahedral structure with the lone pair considering structure, and these 5 can show that the iodine, the electronegativity order is iodine is lowest, bromine, chlorine, then fluorine, then, and this is out of this. So now we considered the one structure. Okay, we consider one structure Pi3, that is this I, and also considers P lone pair F. So considering Pi3 and Pf3, we will discuss about these two, and similarly we can explain this. So now at the first time, the Pf bond are disoriented due to dipole moment, and this is also disoriented. So F is more electronegative than I. So F attracts more the bonded electron pair towards itself, but I attracts itself the bonded electron less than that of the fluorine. So fluorine atom, in this case the fluorine atom, so now as the fluorine atom attracts the bond pair towards itself, so the Pf bond becomes longer, and due to becomes longer, the bond angle become less. Due to the less bond pair repulsion. Again, in the case of Pi bond, the I is less electronegative than fluorine, so the bond length becomes less longer. So in this case, the bond angle will be greater than this. So in this PF3, the bond angle FPF bond angle is about 98 degree, and in the case of Pi3, the IPI bond angle is about 102 degree. So this is. So now we will tell about the fourth case or fourth rule in the VSEPR theory. So the fourth rule is pi bonding effect. Is about pi bonding effect. So what is this? What is pi bonding effect? Pi bond, in general, the pi bond is more fatter than the sigma bonds. That's why the pi bonds contain more the pi bond, because pi bond contain pi clouds, so this is more fatter, and pi bonds create thus more repulsions. That is, more pi bond creates more repulsion, less pi bonds create less repulsions. So let us explain this with an example. The bond order or the bond angle in the case of OF2, OCl2, OH2 should not, I am saying that it will follow in this order, should follow this in this order actually, but it's actually not follow this order. Why is that? Because there, in case of we first say about the correct order. The correct order will be OF2, OH2, OCl2. So why OCl2 have greater bond angle? Due to this, OCl2 have greater bond angle because OCl2 participate in pi bonding. How? Let's see. OClCl. Now these lone pair participate in resonance, and so now these double bond, that is pi bond, one sigma and one pi bond, can participate into the repulsion, and more repulsion occurs and the bond angle becomes more, that is it's about 1 degree. Whereas there is no type of, there is any type of resonance occurs in case of OF2 and OH2. No resonance, that is these two are out of this complex, so out of this order. So the pi bond, in case of pi bond can decrease the bond angle, pi bond increase and decrease the bond angle. When the resonance occurs, the pi bond form and the bond angle becomes greater, and in the case of OF2 and OH2, the bond angle does not depend upon the resonance because it cannot participate in the resonance. Okay, so now the fifth rule and the last rule. So this rule says any repulsive force, that is lone pair repulsion, lone pair bond pair repulsion, or bond pair repulsion, to reduce the bond angle is more significant for the completely filled valence shell than the completely filled valence shell. Now the fifth rule. The fifth rule is any repulsive force between the bond pair lone pair or lone pair, however, any repulsive force to reduce the bond angle is more significant for the incompletely filled valence shell than the completely filled valence shell, because in the completely filled valence shell there is crowding central atom. That is, the central atom is more crowded. More crowded means the central atom is filled with the electrons, but in case of incompletely filled valence shell, the central atom is vacant, or some kind of central atom does not filled with the electron fully. So the one example we can explain, that is NH3 and PH3. The NH3 bond angle is 107 degree and the PH3 bond angle is 94 degree. So this bond angle difference, NH bond angle and HPH bond angle. So why is this difference? We can explain this difference by the fifth rule. Fifth rule says the repulsive force is predominant here to explain this factor. So the more significant factor here is repulsive force, and repulsive force is present there, more repulsive force, and here the repulsive force does not affect the molecule, so there is less repulsion here and here, more repulsion, because nitrogen has valence principal quantum number, valence principal quantum number 2, and phosphorus has 3. Its vacant 3d orbital, and its vacant, there is no vacant orbital, vacant 3d or 3 orbital. So it's a small atom, it's a bulkier atom than n. So it has vacant 3d orbital, vacant 3. Due to this, this vacant 3d orbital easily the electrons is can electron pair in PhD can freely move, the electron bond pair actually freely move. So this can easily retain in the molecule, the bond 3 bond easily move, and 3 bond is free. But in case of NH3, the NH bonds are more repelled due to the crowdedness of the N atom. So due to crowdedness of the N atom, the NH bond is smaller and repelled more. Due to this, the bond angle is 107 degree, and in the phosphorus atom, the center atom, that is phosphorus atom, is less crowded, and due to this, the pH bond, each pH bond are less repelled by each other, and the bond angle is 94 degree, and which is less. So this is the total 5 rule of the valence shell electron pair repulsion theory. So now if you like this video, you can subscribe my channel Easy Chemistry, and I will take the next video with some kinds of another example or another theory or another chemistry topics. So thank you.